solving a system of equations in 3 variables. That's what we're looking at today. We're used to solving equations in 2 variables, and this really isn't that much different. It's just going to be a couple more steps to get us to 2 variables, and then we're going to work on what we've already done before. So it's a couple steps in the beginning that are going to be a little bit different process, and then we're going to get to our system of 2 variables, which we all know how to do. So it's solved the same way. It's just another step, and we're going to use substitution or elimination, which is also known as linear combinations. So I will let you know ahead of time that elimination and linear combinations are the easiest way to go in the beginning, because it's much easier to multiply an equation all the way through to where it adds or subtracts to 0 than it is to solve for a variable and then substitute it in. Unless you already have it solved for that variable, then it's obviously easier to do substitution. So we look at a system of 3 equations. We want to combine 2 of these equations, either like green and purple or green and orange or orange and purple. One of those combinations we want to combine to cancel out a variable. That's going to be our equation number 1. Once we combine to cancel out a variable, we're going to combine 2 other equations and cancel out the same variable. So we have 2 equations with 2 of the same variables that we can solve, because we know how to do that. So the first thing I'm going to do is I'm going to solve right here. I'm going to solve these, and I'm just going to copy and paste this. That way, I can work with it down below. So let's see what we're doing. I'm just choosing this because the x's straight cancel out, so it's easy to add those together. So I'm just going to do this one first. So we got 3x and negative 3x, that's 0x. 2y and 4y, that's 6y. Negative z and 5z, that's 4z. And then 8 and negative 14 is negative 6. So if I just erase this 0x, that's my first equation right there. So now I need to combine either the green and purple or the purple and yellow to drop my x's so I have another equation in just y and z. So I'm going to combine, actually I could do either one of them because I have a single x, so I'm going to be able to multiply by this bottom by 3 to get to cancel out. But I'm going to do these 2. Because the 3 is already negative, and I did not mean to do that. Let's try that again. Copy, paste. Let's move it over here. Alright, so do this one in red. So the first thing I'm going to do is multiply this equation by 3. That way I can cancel out. So this becomes 3x minus 9y plus 12z equals 3 times 14, or negative 14 times 3 is negative 42. I don't know why I went 52. Negative 42. So let's go ahead and add these. Change to red. Alright, so we're adding negative 3x and 3x. That gives me 0x, which is what I wanted. I wanted the x's to cancel out because I want to have y and z just like I had over here. 4 and negative 9 give me negative 5y. Remember, we're adding these 2. We changed that middle one. And then 5z and 12z give me 17z. And then negative 14 and negative 42 give me negative 56. So here is my second equation. This is equation number 2. Alright, so now I have 2 equations in 2 variables, so I can solve. So I'm going to treat both of these equations like something I've had before. I'm going to rewrite them down here. So we have, actually, I'm going to divide this by 2 just to simplify it. If I divide this whole thing by 2, it's still going to be the same equation, just smaller numbers to work with. That's going to be 3y plus 2z equals negative 3. There's my one equation. And then my second new equation is negative 5y plus 17z equals negative 56. Now this is where it gets a little difficult. I can solve for one variable by substituting, so I can solve for z, and then whatever I get for z, plug that into the other equation, that'd be substitution. Or I can do linear combinations. But there's not anything I can multiply one equation by to get the others. Like I can't multiply 3 times anything to get 5 or 2 times anything to get 17. So if I'm going to solve this by linear combinations, I'm going to have to multiply both to get a common multiple. So at this point, it really doesn't matter which way you go. If you do substitution, then you're going to get a lot of real nasty looking fractions. If you do linear combination, you're going to have to do more. So let's just do linear combination, because I like linear combination more, and who knows, maybe you do too. So I'm going to multiply this top times 5 and multiply the bottom times 3, because that's going to give me a 15y and a negative 15y, and those will be able to cancel, and then I'll be able to solve for z. So rewriting my equations after I've multiplied, so this one multiplied by 5, I get 15y plus 10z equals negative 15. There's my first one. And then I'm multiplying this one times 3. So multiplying times 3. So 3 times negative 5 is negative 15y. 27 times 3 is positive 51. And then 56 times 3 is negative 168. Negative 168. Alright, so now I'm solving for these. So let's draw my line here. I'm adding, so 15y and 15y, those cancel. 10z, oh, this should be 51z, I left off a z there. Sorry about that. 10z and 51z, that's 61z. Now hopefully this comes out to be a multiple of 61. Negative 15 and negative 168, that's negative 183. Perfect, that's a multiple of 61. Okay, so now I'm just going to divide both sides by 61, and z equals negative 3. So it looks all bad, it looks all crazy, but in the end we end up with z equal to negative 3, which is a nice, neat integer. Now that I have z equal to negative 3, I know one of my variables. So I'm going to take that value and plug it back into my red or black equation, because I know that I can solve for y. If I plug in z, I can get y. And then once I get y and z, I can plug that back into one of my original equations to find my x. So I know z is negative 3. There's one of my variables. So I'm going to plug this back in. Let's use the black one, because it's a 2 instead of 17. So I'm going to plug this back in, so I get 3y plus 2 times negative 3 equals negative 3. So this is 3y minus 6 equals negative 3. 3y equals 9, negative 9, no, I take it back. 3y equals 3, because I add 6 to both sides. I almost messed up myself there. 3y equals 3, and then y equals 1. So there's my second solution. So now I have y equal to 1, z equal to negative 3, so I can take one of my equations that I started off with, any of these 3 equations up here, and solve for x. So if you think about it, which one would be easiest to solve for x? To me, it looks like the purple one, because x is already by itself. So that's what I'm going to do. I'm going to take the purple one, I'm going to copy it. I can copy a lot faster than you can, and I did that again. I'm going to copy it, I'm going to bring it down here, I'm going to paste it, and I'm going to substitute. So I know what y is, I know what z is, I'm trying to find out what x is. So let's use green. So x minus 3 times y, which in this case is 1, plus 4 times z, which in this case is negative 3, equals negative 14. So x minus 3 minus 12 equals negative 14. So this is negative 15. So when I add 15 to both sides, I get 1. So my answer is x equals 1, y equals 1, and z equals negative 3. But how do I write that? Well, when you solve a system with 2 equations, you wrote it as a coordinate pair. You wrote it as, xy coordinate pair, just like 1, 2 or 2, 2, negative 1, 6. Well, in this case, it's called an ordered triple, which makes sense. There's 3 of them. And we just put them in the order x, y, z. So my solution is going to be, and I'll use red here, my solution to this is the coordinate pair 1, 1, negative 3. 1, 1, negative 3. That means if I take the values x equal 1, y equal 1, and z equal negative 3, and I plug it in to any of these 3 equations up here, any of these three equations, they will all work. They will all come out to equal something equal to like 8 equal to 8, negative 14 equal to negative 14. Each one of them will work. So that ordered triple satisfies all 3 of those equations. All right, and then we have example number 2. So I want you to try to solve example number 2. I want you to take this time, pause the video. We're 11 minutes in, so pause the video, solve it, then come back and then see if you got the correct answer. So hopefully it didn't take you too long to figure out that 0 does not equal negative 8 if you did it this way. If you did a different way, again, hopefully it didn't take you too long to figure out that there is no solution to this. There's a sad face. This is no solution. 0 does not equal negative 8, and 0 will never equal negative 8. So these 2 planes, this is actually 3-dimensional, and these are 2 planes. These planes do not cross. So they are parallel. Or these 2 don't intersect, they might be parallel, and then the red one might intersect them. So if you want to kind of think about the way this works, the visual setting, like you got a plane, then you have another plane, and then there might be a plane that goes through them, or all the planes might be parallel. That's one way to think about it. So I'm getting ready to show you an example of what it looks like in 3D, but this is no solution. Just like in systems of equations, when we have parallel lines, if we have parallel planes, there is no solution. So if we scroll down, we can see a physical representation of what this means. When we talk about 2-dimensional, we talk about lines. We talk about x, y, 2 points make a line. When we talk about 3-dimensional, we look at 3 points. 3 points can make a plane. You dealt with planes and lines and all this stuff in geometry. When we have 3 planes, we have an x, y, and z plane. You're used to the xy coordinate plane. That's 2-dimensional, but when we throw in a z, that makes it 3-dimensional. And here are your possible solutions. When all 3 of these planes intersect, like this, that's infinite solutions. That means it is a line. When they intersect like this in the middle, that's one solution. That's like the first that we got. That's a point, one single point in 3D space where all 3 of these planes intersect. And this is just one way we can get no solution, and that is if all 3 of them are parallel. We could also take this last plane and turn it and make it perpendicular through these other 2 planes, and that would also be no solution because plane 1 and plane 2 would not intersect. If plane 3 was running perpendicular like this, then plane 1 and plane 2 would still not intersect, but you might find a solution between these 2 systems. But then once you found a solution between these 2, you would see that they don't intersect, therefore there are no solutions. And that's it. So tomorrow we're going to talk about matrices and solving systems of equations with matrices, and you'll find out how much you actually really do love matrices.